Thank you. Thank you, Martin, for the introduction. Yeah, so I want to say this work was done in collaboration with Elena, Eric, and other people. And so I'm thankful to the US NSF Career Grant that supported us. Okay. And so the goals of the project are threefold, but I'm only going to tell you about two because of time. And so basically, we just wanted to calculate the excited states of the Lipkin model on a quantum computer. And we also wanted to look at something very interesting in the equation of motion framework. What happens when we increase the complexity of the excitation operator? And so another thing which I will make a claim and I won't have time to show you is that there are better ways to efficiently encode the Lipkin model on a quantum computer. All right, so the outline of the talk will just follow the basic goal of the project. I will show you how to encode this Lipkin model on a quantum computer, give you a little bit of background of the quantum equation of motion, and show you how this works out in action. All right, so for those who are living under a rock and maybe are not familiar with the Lipkin model, so it's basically a two-level system. Each energy level is N4 degenerate, and this is the Hamiltonian for it, where these operators satisfy the standard quantum spin, quasi-spin operators, and you can find more details of it over here. And so now I want to show you how do you encode this Lipkin model on a quantum computer. You basically have three ways, but I'll only show you two because of time. So the first way is to just look at the fermionic occupation number basis. That means at each site that you have where the fermions can live, you can either look at either occupied or unoccupied, and then you take the fermionic operator, do Jordan-Wigner transformation. This turns out to be a bad idea for obvious reasons. If you look at the size for n equals to 2, the Hilbert space gives you a metric that's a 16 by 16 metric. This is not a very good encoding scheme. Can we do better? And yes, there is a better encoding scheme. This is the work done by Michael and his team. This paper was published in July this year. And so I'll just show you for the W equals 0 case. And so what they did is to rewrite the Hamiltonian in terms of individual spin bases. And there's an advantage of doing that because automatically you find out that your Hamiltonian it's now written in terms of your Pauli matrices, which is nice. No need to do Jordan-Wigner transformation. And instead of 2n qubits, you now need n qubits. And so your metric ends up becoming a 4 by 4 for the n equals to 2 case. And I want to make a claim, I don't have time to support it, that there is a better way to encode this. And for the n equals to 2 case, we can actually use 1 qubit. And the way to see about it is that this metric has zeros, which these zeros can be eliminated. And so, yeah, that's the short intro. But I won't give you details of that. Yeah. So the equation of motion, as a refresher, if you are familiar with it, the formulation is this: given the ground state, can you calculate the excited state? And the answer is yes. What you do is you define an excitation operator, and from that excitation operator, basically you do a little bit of algebra and you can convince yourself that you can come up with this equation, which we call the equation of motion. And so the idea is that if you can solve this equation of motion, you can find all your excited state energies. And so how do we do that? The way we do it is first, the ground state, it's not given from above. You just guess it using some form. And the next thing that you do is the excitation operator. You write it as a linear combination of basis operators. For example, fermionic creation and annihilation operators. And so that ends up looking like that. Those are the details. And basically, you then do the minimization of the equation of motion. And then what you end up finding is this equation. which is the generalized eigenvalue equation. And so the goal, what we're trying to do now is how can we use quantum computers to solve this equation, whereby these matrices are just the expectation value of these commutators. And so this is the work done by Pauline and the IBM Zurich group. And so they introduced this last year, actually. I think it was 2019, and then there was revision in 2020. What they call the quantum equation of motion. And so how does that work? The first thing is that you can now have a system of finding the ground state. And so the ground state, we find it using VQE, the variational quantum eigensolver. If you've been in many of these talks, you already know what that is. And so once you find your VQE, which is described here, you then now go on and do an expectation value of all of these operators. And then once you have that, you can now solve this equation classically. And so it's not entirely a quantum algorithm, it's basically taking parts of the procedure and quantizing it for obvious, to get better performance. And now it turns out it's much more efficient to do expectation value on a quantum computer than you would in a classical computer. All right, so let's see how this works in action. The first thing to do VQE, what we need is an ansatz. And so let me show you an ansatz that, this work was done by Michael and his team. If you write down the Hamiltonian for this explicitly, you end up finding, for the n equals to 2 case, that you only have one variational parameter. And so what we do is that variational parameter, before I go to the results, what we do is we take a line search on all the space of VQE and then sort of find the minimum of that variational parameter. And so now let's look at the results. They turned out to be better than we would expect, particularly on current quantum computers. And so here we have the energy in the y-axis, and here we have the effective interaction strength in the x-axis. And so what we did is we calculated the ground state using VQE, and then we use the quantum equation of motion to calculate the excited states. And I need to tell you that we use second RPA, which means alpha equals to 2, because we have got 2 excited states. And so this is the results of that. And we compared 2 regions of this, as you can see with the line. This is the region where you have low coupling, and then we go to a higher coupling regime, and we start to see something very interesting happening there. And this zigzag can be explained if we also look at the graph of the angle phi, the one that we are optimizing for the ansatz. And so what we thank you for the one. And so what we see here is that as you go in this higher interaction strength, you get a little bit more effects, and so the algorithm becomes more sensitive to deviations from the ideal. So this is an ideal angle that we find using an optimizer, and so we can look at the device. This is where you get big deviation, and that explains those results there. All right, so the other thing that I told you about is that we are interested to look at what happens when we increase the excitation complexity. For RPA, it's alpha equals 1. For second RPA, it's alpha equals 2. That means 1 body and 2 body. And so if we look at the results, we can only compare the first excited state, so we can compare RPA and second RPA. We see that the second RPA calculation performs much better than the RPA calculation, but we also see that we get more noise as we go to strong coupling regime. And so just for fun, you can also compare the ground state, and we see that the ground state for n equals to 2 is much better than the RPA and the Hartree-Fock calculation. And so this could be something interesting for those studying small systems. All right, so let me summarize. There are a couple of points here. The one that I want to emphasize is that this method is sensitive to deviation of the parameter that you use to optimize from the true optimum one. And so there's a much more work that needs to be done in studying error propagation. How does the error from the ground state propagate to the excited states, and how do you mitigate for that? And so with that, thank you for listening. I can now take questions. That's a very good question, because we're currently exploring n equals 4, and my feeling for that is you have two regions. One is the low coupling region, and the high is high coupling region, and so you get more degradation there. But for the you get a little bit something as you expect in the low effective interaction strength. And so, yeah, there's more sensitivity to the noise as you increase the number of particles and the interaction strength as well. Thank you. Wow, so everybody's interested. Well, wait for the paper. Wait for the paper. Okay. All right, thank you.